Thank you, everyone. It's fun to be giving a talk now in this series after coming in and watching a lot of the talks throughout the semester. Really great to see all this nice planetary science work, both at Penn State and people coming in from outside Penn State to talk about what they're doing, right? So I'm going to talk about a few different ways that the planetary interior and the dynamics of a rocky planet's interior affects the surface environment and kind of sets the stage and some of the conditions that are suitable for life, right? So this is one of my really favorite one of the biggest things that I work on in my research, right? And hey, there we go. Right. And so I just, to kind of explain like how I got into this topic, right? I just wanted to give you a little bit more background on who I am and what I do, right? And, where this idea of thinking about the interior dynamics effects on the atmosphere kind of comes from, or at least how I got into it, right? So I call myself a geodynamicist or mantle dynamicist. I'm really interested in the interior of rocky planets like the Earth and how they evolve over time. And so I use a lot of computational tools, right, numerical models or other kinds of models to understand mantle convection on Earth and other planets, right? And so like I really got into this field because I was really interested in what causes plate tectonics on Earth. I actually remember being an undergraduate student at USC, learning structural geology and thinking, great, I'm going to understand. They're going to tell me everything about how plate tectonics works, right? I can't wait to hear this. Right, and the professor telling me we don't know why Earth has plate tectonics. Like, how can that be? We've understood that plate tectonics has been happening for like 50 years. How can we not know why there's plate tectonics on Earth? So that kind of got me going, right? And that's been a major topic I've worked on, in my research as a grad student, and then through on after that, right? And we still don't know the answer, right? If I figure out the answer, it'd be great. It would make me famous. But then also, what would I do after that, right? We've got to have these problems that we all chase, right? So I'm interested in that, and also how tectonics has evolved on Earth using convection models like this one, right? And as I got into working on this as a grad student, I started off thinking, not recognizing the connection to astrobiology and habitability of planets at all, right? But then the more and more I learned about this, the more I realized that there are really important connections between this kind of mantle convection dynamics happening in a planet's interior, right, to the surface environment and what's setting the stage for life, right? Mainly connected through cycling of elements, right, between the planetary interior and the surface through volcanism, weathering, breakdown of rock to the surface, and processes like that, right? And so that's the part I'm going to talk about today, right? And that's another major aspect of my research that's developed in the last, few years, and something that's, a really fun and really exciting topic to work on. Okay, so the main point of this talk is going to be looking at ways that the planetary interior and its evolution affects whether the planet can be habitable for life, right? So in order to do that, we've got to first think about what kind of things are important for life, right? So if we think about what kind of factors are important for a planet to host life, and we're going to restrict this to Earth-like life, right? Life as we know it on Earth, right? Then there are a few things that kind of jump out. I've got like a useful list. I'm sure certainly an incomplete list, but at least something for us to kind of go on and think about these connections between the interior and the surface, right? So what does life on Earth need, right? We think we need liquid water, providing a solvent for the kind of reactions that are important for metabolism and potentially for the origin of life as well, right? We think we need a certain kind of temperature range, right? So we've found organisms that can live at some extreme environments up to very high temperatures, above 100 degrees C, low temperatures, but there's still a range, right, where we think, or at least, of the life we've seen, that, life can't really survive and thrive outside of these ranges, right? And we also think we need certain elements, bioessential elements, right, that are important for the kind of building blocks to life, like DNA and other kinds of things like that, right? And so these are often called the SNOPS elements, right? Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. In my planetary habitability graduate student class that I'm teaching this semester, some of us have taken to calling it SPONCH, SPONCH, which I kind of like, right? It's almost a little easier to pronounce than SNOPS, and also sounds really funny. So whatever, whichever way to pronounce it, right? Those are really important elements that we think are important for life, right? And their availability is going to be controlled, at least in some ways, by this cycling of elements between the interior and the surface. An important caveat, and really, like, there's lots of caveats we could include even on that slide, right? But one important caveat is we can think about, do these conditions that I've laid out as being important for life, do they need to exist at the surface of a planet for that planet to be habitable, right? Or is any place in that planet's interior, where those conditions are met, a place where life could exist, it could be considered habitable, right? So, you've heard talks already this semester about icy moons in our solar system, like Europa and Enceladus, right? So these are places where the surface doesn't seem particularly hospitable, right? At least to life as we know it, it's frozen over, right? But beneath this ice shell, there's liquid water, potentially in contact with rock, right? Potentially providing the right temperature, right? The presence of water itself, and potentially with interaction with the rock beneath, maybe some of these schnaps or sponge elements that we think we need for life, right? So when I talk about habitability in my talk, right, I'm going to focus a lot on planets outside our solar system, so exoplanets, right? And an important consideration with that is planets where we think if life was able to develop and start affecting its atmosphere and leaving behind some signatures that we could detect, right, we're going to be looking at these planets with telescopes, right? Telescopes either on the ground or in space. And we're going to be looking for signatures of life existing probably in that planet's atmosphere, right? Or maybe some sort of clear signal coming from the surface, right? So in that case, it's going to be much easier to detect if the life is on the planet's surface rather than beneath an icy shell. So I'm going to focus on the conditions that allow surface life to develop on planets, right? But you should have in the back of your mind, right, the planets I'm calling not habitable. I'm thinking about habitability in terms of the surface of the planet, right? So planets that are, what I might consider too cold to be habitable might still be able to host life in some subsurface environment, right? So we shouldn't, rule those out, in the kind of broad sense of thinking about habitable planets, right? That's probably also a good point to make the caveat that, this list of things that are important for life, right, that I'm going to use as kind of a guidepost for my talk here. This is all for life as we know it on Earth, right? So it's possible that there's life as we don't know it, right, that uses different kinds of reaction pathways, different kind of chemistries to do its thing, right? And maybe some of these requirements for life might be different or relaxed, right? And so, again, I'm going to focus on what does it take for a planet to meet these requirements for life as we know it on Earth, right? But that's another just, keep your mind open, right? Not just today, but kind of the whole rest of your lives as you hear about searches for life outside our solar system, right? Or even within our solar system, as thinking about, life might surprise us. It might be types of life that we don't understand yet, right? And so really, I kind of advocate for looking at everything, right? We should be looking at as many different types of planets as we can to try to understand whether they have life, right? Okay, so let's think about what it would take for a planet to meet these kind of requirements, right? That's going to be our guidepost today for thinking about life as we know it on Earth, right? So I've listed two things that are really kind of climate related, right? So having liquid water on the surface and having a suitable temperature range, right? For the range of temperatures that we've seen any sort of life on Earth be able to kind of thrive in, right? And reproduce in, right? So those are both connected to climate, right? And that means they're going to be affected one by, or controlled one by the amount of solar radiation the planet's receiving, right? So that linked to its position or distance from the star it orbits, right? But they're also going to be connected to things like the greenhouse effect, right? Which is going to be connected to geochemical cycling between the surface and interior, right? Giving the kind of interior control on that, right? And then the other thing I've listed here is these bioessential SNOPS elements, right? And these, right, and being in abundances at the surface where life could, use them, right, is also going to be in large part controlled by the surface interior geochemical cycling, right? So that's one of the main kind of factors where the interior starts to play a big role in how the surface environment develops, right, and whether we can develop conditions that are habitable for life. Right? So, what does it take for a planet to have the right kind of conditions for liquid water in a temperate climate, right? So one of the most important things, right, is really just where a planet forms, right, and the amount of sunlight or starlight that planet's receiving, right? So there's a concept that was really pioneered by people here at Penn State, Jim Casting, who recently retired. Basically, if you ever see a cartoon or picture of what we call the habitable zone, this range around a star where the amount of solar radiation coming in we think is right for liquid water to potentially exist on the surface, really good bet it was either made by Jim or came from people using Jim's kind of methods and ideas, right? So what this does is it tells us that we've got these limits, right, on the amount of starlight a planet can be receiving and still potentially have liquid water, right? So we've got this range in here, right, called the habitable zone. If a planet's too close to the star it orbits, right, in here, right, then the amount of starlight coming in is so high, right, there's so much energy coming in, right, that it's basically impossible, we think, for liquid water to ever condense and form oceans on these planets, right? So the oceans would basically boil away, right, and we'd have no chance of having the kinds of conditions we think are important, at least for Earth-like life. Right? If you go to the opposite end of the spectrum, right, you can find a limit where there's so little energy coming in from the sun, right, that even if you can put as much CO2 in the atmosphere as you want, you still can't keep the climate warm enough, right? The atmosphere can kind of collapse in on itself, right? And these planets would freeze over, right? So out here, it's too cold, and here it's too hot. And in here, we've got what's also sometimes called the Goldilocks zone, right? Where things we think are really just right, right, for planets to be able to have liquid water, right? This is all well and good, but even with this habitable zone picture, I think at least defines kind of a good first pass of where planets might be able to have liquid water, right? There's still additional things that have to be happening for a planet within this habitable zone to actually still have a temperate climate that's suitable for life and suitable for liquid water, right? And that's because if a planet is sitting really close to this inner edge, where it's receiving lots of energy from the star it orbits, right? It's got all this stellar energy coming in. It needs to have a pretty small greenhouse effect, very little greenhouse warming. And here, for the climate to still be cool enough for liquid water and for life. The planet's sitting way out here, really close to this outer edge. So it's receiving a small amount of energy from the star it orbits. Then it needs lots of greenhouse warming, right? So maybe lots of CO2 or other greenhouse gases in its atmosphere for the temperature to be warm enough for liquid water, right? And within our kind of nominal zone that we think is important for life, right? So even planets within this habitable zone need some sort of kind of regulation of their climate and their greenhouse effect to actually have a temperate climate that's good for water and good for life. So what is that regulation, right? So we think this regulation comes from this cycle that's been really well studied on the Earth called the carbonate-silicate cycle, right? And this carbonate-silicate cycle controls the amount of CO2 in Earth's atmosphere over geologic timescales, right? And we think should apply to other planets that at least have, kind of similar compositions and kind of dynamics of Earth, right? And I'll go through my talk and talk about some of the extreme situations where this may or may not apply, right? Okay, so how does this work? We've got carbon cycling between the surface and interior, right, through volcanoes, right? So I've drawn this like a plate tectonic Earth. So we've got, volcanoes around subduction zones, around plate spreading ridges, around hotspots like Hawaii, right? This melting that creates these volcanoes is also taking volatiles like carbon and hydrogen that are locked in Earth's interior and releasing to the surface as gases, right, where we can get on our oceans and also release CO2 to the atmosphere. At the same time, there's weathering, so breaking down of rocks on the surface or of the seafloor, right, that is taking CO2 out of the atmosphere, right? So these rocks are dissolving in kind of slightly acidic rainwater or slightly acidic ocean water as carbon dissolved into the oceans, right? That breaks these rocks down, right? Releases ions that then form carbonate minerals, right, in the seafloor. And effectively, we're taking CO2 from the atmosphere through this dissolution weathering process and locking that CO2 away as carbonate minerals in the seafloor, right? So that's a long-term removal of CO2 from the atmosphere, right? And then the two rates of these CO2 going to the atmosphere from volcanism and being lost from the atmosphere from weathering is what controls CO2 in Earth's atmosphere over very long time scales, like millions of years, tens, hundreds of millions of years, even going back billions of years throughout Earth history, right? And so this process has some key stabilizing negative feedbacks that help it regulate Earth's climate, right? And so if the climate gets cold, this weathering process slows down, right? While volcanism doesn't really care about whether the climate's cold or not, so it keeps, spewing CO2 back out in the atmosphere. We can build CO2 up in the atmosphere and start kind of counteracting this climate cooling and warm the planet back up. And vice versa, if climate gets really warm, this weathering rate increases, right? We pull CO2 out of the atmosphere more quickly, right? Then we're putting it back so we can get the CO2 level to come back down, right? This provides a nice stabilizing feedback, right? That can create this kind of regulation that we're looking for, right, throughout the habitable zone. So here's a demonstration of this regulation process in action, right? So we're looking at the starlight a planet's receiving relative to the present day Earth, right? That's one, right? So if we go back to lower solar energy, right, the negative feedbacks in the carbonate-silicate cycle allow more CO2 to build up in the atmosphere, right? That's these lines, right? And that keeps the climate warmer than it would have been without this cycle, right? So climate would still be like a little cooler than it is today with less solar energy coming in, right? But it's not frozen over like it would be if we didn't have this negative feedback, right? And then as the solar energy increases, this feedback is sort of naturally drawing CO2 out of the atmosphere, right? And allowing temperature to not shoot up as much as it would without this feedback. So the dashed line is an example of a planet without this kind of feedback. right? Temperature shooting up into a warm regime, right? Where we lose water pretty quickly, right? Without CO2 being regulated in the atmosphere. A big question I'm interested in to really start linking this to interior dynamics of planets, right? Is what does it take for this feedback to fail? Does it always work, right? And always perfectly regulate planets or not, right? So there are a lot of ways this feedback can fail, right? And it can fail in terms of things like the rate at which CO2 is being released from the interior, right? Which comes down to rates of volcanism on planet and over time, right? And the rate at which we're producing crust and fresh rock at the surface to allow weathering to happen, right? So this is mapping out climate states, right? So warm would be, just right, something that's suitable for life. Right down here would be planets that are totally frozen over, we call snowball planets. So I think Earth has been in a snowball state in its past, right, where the whole surface froze, right? And then we've got really warm climates, and then runaway greenhouse here is where, we boil away the oceans, right? At some point, we're not going to be able to prevent this forever, right? Because at some point the sun will warm up so much that we can't really stop for that anymore, right? Okay, and we're looking at this in terms of, again, the solar energy we're receiving normalized to today. So one is what Earth's receiving today, right? And then also looking at this in terms of the rate at which CO2 is being released from the interior through volcanism, right? Again, also normalized to the present day Earth, right? So this is the rate at which CO2 is coming out of volcanoes today, right? 10 times higher, 10 times lower, right? And you can see there's regions where the CO2 degassing rate, even with this carbonate-silicate cycle trying to work and trying to stabilize the climate, it's still not enough, right? And the planet would freeze over, right? So if CO2 degassing is too low and solar energy is low, right, then a planet can freeze over. So the degassing rate is going to be really important for whether a planet can stay in this just right warm zone, right, even with the carbonate-silicate cycle trying to work. Right? And then another factor, which actually isn't shown on this graph, but I've looked at this myself in the past, it's if you shot way up above this, the top axis of this graph here, you'd reach a point where actually there's too much degassing. There's so much CO2 coming out of volcanoes in such high concentrations, right, that even if you completely weathered and altered all of the surface rock that's available at that moment to try to bring this CO2 out, right, it's not enough. And we just keep piling up CO2, more and more CO2 in the atmosphere. And the climate would go into a really hot house, almost like Venus-like kind of state, right? So we've got to look at these kinds of balances to figure out what does it take for planets to kind of sit in this, happy Goldilocks Goldilocks zone versus falling into these end members where they'd be too cold or too hot. So I'm going to try to talk about three things here if I have time, right? And the first two are going to be related, right? And the first two are really going to be thinking about the role of planet's interior evolution and tectonics, right? So one of the things I'll motivate here in a little bit is, this kind of picture that we drew for how the carbonate-silicate cycle works on Earth. I've drawn it tied to plate tectonics. Here's a subducting plate and a spreading ridge and all this kind of stuff, right? But what about planets that don't have plate tectonics? Can this process still work or not, right? So we'll look at that. And I'm going to say that I think this actually does work without plate tectonics as long as we've got active volcanism, right? And then tied into that is, based on the results of this work, right? And then natural question that I've worked on more recently, right, with a colleague where we tried to try to constrain like how much heating power there could be in rocky extrasolar planets outside our solar system, is how long could these habitable climates last on non-plate tectonic or stagnant-lid planets, right? So we'll talk about that. And then hopefully I'll have time to show some work at the very end, right? Some really brand new work from one of my students, Adam Stone, sitting in the back there, right? On waterworld planets, so planets that are totally covered in the ocean, right? And whether they can still be habitable or not, right? So I want to acknowledge some of the people I worked with on the stuff I'll show you today. So the first part, I worked some with another Penn State colleague, Andy Smyth, who's a metamorphic petrologist, right, to help constrain the kind of important process of crustal burial on the stagnant lid planets I'll talk about, right? And the middle part, where I'm looking at the thermal evolution of these planets, I worked with a number of people, but the main one who really helped develop the ideas is this guy, Cayman Unterborn, right? And we helped link astronomical observations to our thermal evolution models, right? And then for this last part, I already told you about my student, Adam Stone, who's here, and this is collaborating with another Penn State faculty member, Kim Lau, who's more of an expert in these kind of water rock reaction models that I'll show, and we're both kind of co-advising Adam on this project. So why should we think about planets that don't necessarily have plate tectonics, right? So plate tectonics is just one type of tectonics that a rocky planet can exhibit, right? And it actually turns out that Earth is the only one that we really know of that has plate tectonics, right? So the other kind of end member, right? So of course, with plate tectonics, really to me, the kind of defining feature of this is subduction, right? Where we've got a lithospheric plate, including the crust and the lithospheric mantle, right? That can subduct down, sink down into the interior, bring material back into the interior. And it's that process that's really driving motion of the rest of the plate to the surface, right? But, the other kind of end member, right, that we see certainly on planets like Mars and Mercury, potentially on Venus as well, is something we call a stagnant lid, right? And the stagnant lid's kind of illustrated by these two diagrams, right? So instead of this surface, lithosphere being broken into separate plates that can interact and converge like this, we've just got one lithosphere covering the whole planet. And there's still convection happening beneath this lithosphere, right? But it's not, causing the lithosphere to break into chunks and to move around, right? There's still volcanism on stagnant lid planet. So you shouldn't think of stagnant lid meaning like it's dead and nothing's happening, right? There's a convecting mantle, right? There's potentially dynamics of like the lithosphere and crust kind of dripping off in little blobs from the bottom of it to help drive this convection. There can still be mantle plumes, right? Like hotspots like Hawaii that create volcanism, right? But we don't have subduction. Given that plate tectonics is just one possibility, right? I think it's important to then think about what would happen in terms of volatile cycling and habitability, potential for habitability on planets that don't have plate tectonics. And if we look at our neighbors in the solar system, I've kind of already said this, but there's a picture to really drive it home. The only one we know of that for sure has plate tectonics is Earth, right? Mars is pretty clear that it seems to be in a stagnant lid regime, right? The surface hasn't really done much for billions of years. Mercury, right, the same. Venus might actually be kind of in between. Like there's some parts of Venus that look sort of like, subduction or kind of similar types of deformation to Earth, but it clearly doesn't have a full like global network of tectonic plates the way Earth does, right? So we've got, it's hard to say much with just 4 rocky planets in our solar system, but if we just take those statistics, 1 out of the 4 has plate tectonics, right? It might not be super common, right, among rocky planets in general, or at least we should think about, whether plate we certainly shouldn't take for granted that when we're looking at exoplanets that they're going to have plate tectonics. So I've done some work over the years to try to figure out, try to develop like what kind of processes in terms of carbon cycling, right, would happen on a stagnant lid planet, and is this going to be able to provide the same kind of stabilizing feedbacks that work on Earth, right? So the basic way we map this out is, if we think about, we've got a convecting mantle on a stagnant lid planet, right? That's still, at least early on when the planet's warm, causing melting and volcanism. And this volcanism will release carbon that was stored in the mantle to the atmosphere, right? Providing a source of CO2 to the atmosphere, right? For all this work, I'm going to focus on planets that are sitting within their respective habitable zones, right? And basically we're looking at, okay, even if a planet's in the habitable zone, right, does it have the right kind of interior processes to drive the carbonate-silicate cycle to really allow it to have a long-term temperate climate, right? So assuming these planets are in their habitable zones, right, if there's liquid water at the surface, we can have weathering, right, that will carbonate the crust, take some of the CO2 out of the atmosphere, right, and put it in the crust, right? And then on a stagnant lid planet, we don't have subduction, right? So we're not going to return carbon to the interior that way. But instead, what will happen is, as volcanism continues, it just piles up on the surface of the planet and basically just buries the crust that was there before, right? And we just get this thicker and thicker pile, right, of volcanic crust, right, each with some carbonate in it from the weathering we had at the surface, right? And eventually this carbonated crust, right, can do 2 things. It can either founder, right? In other words, it can like blob off and sink down into the mantle, right? Or we can reach temperature pressure conditions, right, where the carbonate minerals in the crust would break down and want to release their carbon back to the atmosphere, right? And that would cause what I call metamorphic outgassing, right, of carbonated crust rather than volcanic outgassing, which is coming directly from carbon in the mantle. Right? Okay, so I want to ask like 2 main questions here, right, that are then going to tie into whether the carbonate-silicate cycle can operate and regulate climate on these planets, right? And those questions are whether outgassing, combining both of these sources, is enough to keep the climate warm, right? Or whether it's too low and we end up in this snowball state we talked about, right? And the other limit is wanting to make sure we don't get too hot. Is there enough rock being created, right? So we've always got fresh rock at the surface that can be weathered, that can draw the CO2 out of the atmosphere that we're putting in through volcanism and metamorphism, right? All right, so I'm going to do this using, all right, thermal evolution models, right? And these are models where we track a basic energy budget of Earth's mantle, right? And we're going to think about, or it's not Earth anymore, right, of a rocky planet mantle. And we're going to think about heat being produced internally through radioactive heating. It's one of the main heat sources in Earth's interior, right? Heat coming in from the core and heat leaving from the surface, right? And we can balance these together in a nice budget, right? Which then mathematically will look like this, right? And will allow us to model the time evolution of temperature in Earth's mantle, right? Based on these sources of heat, right? Heat production, heat coming from the core, right? And heat being lost through the surface, right? And actually the real model I'm going to use is even simpler than this. I'm just going to ignore heat coming in from the core, right? And just look at heat being produced internally by radioactive elements and being lost through the surface, right? And that's because on an Earth's heat budget, I mean, like newer estimates are starting to get, a little higher for the heat coming out of the core, but it's generally thought that radioactive heating is kind of the dominant heat source on the Earth, right? And heat coming in from the core is a smaller component. In order to track this, right, this is taking an approach where I'm going to use kind of simple parameterizations, right, to track these heat fluxes and how the temperature of the interior evolves over time, right? And the main kind of trick of this, or like, biggest part, is a parameterization for the heat flux from mantle convection, right? So that heat loss term, right? And we've got scaling laws and kind of theory from lots of work on this over the years, numerical models, or lab experiments, right, that show us that basically when the mantle is hotter, right, or convecting more vigorously, right, we get a thinner lithosphere, right, where the temperature, right, is following a steeper gradient, right, and we get a higher heat flux, right, in these conditions where the convection is acting more vigorously, right. When convection is less vigorous, right, we end up getting a thicker lithosphere, a thicker kind of surface lid that leads to a shallower temperature gradient, right, and that means we get a lower heat flux. Right. And so then this links to mantle temperature, right? Because when the mantle is warmer, right, we expect the viscosity of the interior to be lower, more vigorous convection, and a higher heat flux. And the heat flux decays as the planet cools off over time. Right? That was one individual model, right? We can take a bunch of these models at different conditions and try to map out, okay, when did the climate stay warm enough based on this balance of we're releasing CO2 to the atmosphere from volcanism, right? We're bringing it down from weathering, and we're not hitting these two limits of too little CO2 outgassing so the climate gets too cold, or too much CO2 outgassing versus not enough fresh rock being produced and climate gets too warm, right? So we can kind of map this out, right? And I mapped it out in terms of the lifetime in billions of years that habitable climate lasted as a function of the total carbon budget of the mantle, right? Which is going to be determining like how much CO2 outgassing we get, right? If there's lots of carbon in the mantle, then a little bit of volcanism makes a really high CO2 outgassing rate. If there's very little carbon, right, then even lots of volcanism, you don't necessarily get a very high CO2 outgassing rate, right? So that's one of the key factors controlling this, right? And another big one is the heat production rate. And this is the heat production rate in terawatts. That's kind of the typical unit to use for measuring heat production on a rocky planet like this when the planet is born, right? When it starts, right? And then it starts cooling off after that, right? So we get this sweet spot here in the middle, right? Where everything's kind of just right. And we get habitable climates lasting increasingly long, right? So 1 billion to up to 4 or 5 billion years, right? For planets that have lots of heat producing elements. About 100 terawatts is like Earth-like, right? So a planet that has twice as much radioactive heating as the Earth, would plot up here, right? And so, as it's hopefully kind of intuitive, the more radiogenic heating power a planet's born with, right, which is going higher up on this y-axis, right, then the longer volcanism can last on that planet, and the longer we can drive outgassing and carbon cycling to keep the climate stable and warm, right, and temperate, right? So habitability lifetime lasts longer as we go up the y-axis, right? And then we've got these two limits, right, where we've got a Goldilocks zone where it works, right, and then a limit where it's too cold, and a limit where it's too hot, right? And this is being controlled by this carbon budget, right? And basically, a planet sitting out here, even if it has lots of volcanism, got so little carbon in its interior, right, that there's hardly any CO2 coming out. There's just not enough carbon to make CO2, right? So that planet gets too cold and would freeze over, right? Because we're just not putting enough CO2 in the atmosphere, right? The other extreme is out here, right, where a planet has so much carbon, right, that as it as volcanism happens and we release this CO2 to the atmosphere, we're releasing it at such a high rate that we can't bring it all down, right, by weathering the rocks we're producing. right? And so this is a place where the outgassing would overwhelm the weathering, right? And CO2 would just build up and build up in the atmosphere, and the planet would get really hot, right? So we kind of break the cycle on this side and on this side, and then here things are working just right and allowing the planet to stay habitable. Right? Okay, so that kind of was like a proof of concept, demonstrating the kind of limits where this carbonate-silicate cycle, I think, can work on a stagnant-lid planet, right? And some of the big factors we saw, right, were the carbon budget, basically how much carbon does the planet acquire when it forms, right? So that would be, if we could figure that out for other planets, that would be an important thing, right? And the other big factor was the heat budget, right? And so that's the amount of like radioactive elements the planet acquires to power its thermal evolution and volcanism over its history, right? So figuring out how much carbon an exoplanet has is probably going to be really hard. I don't really know a good way to do it, right? But the heating power is a little more tractable. And the reason is we think we can use the measurements in stars, right, that host planets to try to say something about the composition of the planets that orbit them, right? So this is where I teamed up with this colleague of mine, Cayman Unterborn, right, who's thought about this problem himself over the years, right, and tried to make measurements like this, right? And there's databases where people take measurements of star chemistries, right, and compile them, and we can kind of mine them to try to look at what kind of variability of star composition there is out there in our galaxy, right? So, right, what we looked at is what is the range of heat-producing elements, right, seen in stars, and can we use that as at least some measure of the kind of probability uncertainty of heat-producing elements that planets out in our galaxy might acquire when they form and power them, right? So we've looked at measurements of thorium, right? So one of the main heat-producing elements on Earth is thorium-232, if I remember the number right? Right, it's a very long-lived radioactive element, right? The other main heat-producing elements are uranium-235 and 238, and then potassium-40. Uranium, it turns out, is really hard to measure in star atmospheres through kind of normal spectroscopic techniques. So what people do is they look at europium and use that as a proxy for uranium because they're thought to form in the same way in nucleosynthesis and kind of are supposed to always like match each other in stars, right? So we used europium as a proxy for uranium, right? And then potassium is also measured as well, right? And we use that, right? And so what we have are these probability distributions, right, that are essentially log normal distributions each, right, representing the kind of spread in the heat-producing elements that we see at least in stars, right? And so what we're going to do is we're going to make a little bit of a jump, but hopefully not too unreasonable jump, and say, let's assume that these probability distributions that we see in stars are going to match a probability distribution of these heat-producing elements in planets, right? So basically, we're going to take these distributions and run models where we draw randomly from these probability distributions of these heat-producing elements, thorium, uranium, potassium, right? And use those to drive the models and see, okay, like kind of probabilistically, right, how long do we expect volcanism and outgassing to last on these stagnant-lid planets? And therefore, about how long do we think this climate regulation, right, through the carbonate-silicate cycle can last as well? Okay, so basically, we're going to treat these distributions as reflecting the sort of like system-to-system uncertainty around the galaxy of how much radioactive heating a planet might acquire through its planet formation, right? So we use that. We'll also sample from uniform distributions of other parameters that are important and can't really be constrained, like the initial temperature of the planet, right? Interior, which tends to not matter too much, and then the what I call the reference viscosity, right? So that's the viscosity of the planet, reference to like present-day Earth conditions, right? And that's also something we can't infer very well for other planets. It does have a big effect, right? And so we're going to just use a uniform range over kind of a reasonable range of numbers here to show how that effect comes into play. All right, so this is kind of the basic results from our models. So we ran, at kind of we picked different planet masses, right, from Earth mass up to a few Earth masses, right? And at each planet mass, right, we ran a huge number of Monte Carlo type models where we randomly sampled from these different distributions, the heat producing element distributions, and also the uniform viscosity distribution, right? And then we logged basically how long did volcanism and therefore carbonate-silicate cycling last on these planets, right? And use that as a baseline of, about how long habitable climates might be able to last on these planets, right? So this range here, right, is the kind of uncertainty range we get based on the sampling across these different parameters that are driving the model, right? And the points in the middle are basically the average for each planet, right? So we did that for these different masses, right, and produced this general trend, right? If we see a very large spread, right, in the age in billions of years, right, that volatile cycling can last, right, on these planets, and a general, like not real strong, but a slight increase with increasing planet mass, just from the fact that bigger planets tend to hold on to their heat better, right? They tend to cool more slowly over time. Right? Okay, so we can split this up in a few ways. And in one way is to kind of see like what are the really important factors controlling this, what we call degassing lifetime, or maybe I could call it volatile cycling lifetime, right? That we think is important for habitability of these planets, right? And so we've mapped this now, right, with degassing duration or lifetime here, right, in billions of years, right, going from short-lived to longer-lived, right, and from red to purple as a function of now this viscosity, right, what I call the reference viscosity, right, and then the heat budget the planet acquires, right here normalized to an Earth-like planet, right. So down in the bottom corner, we've got planets that just through the luck of the draw ended up acquiring, small endowments of the radioactive heat-producing elements, right. We also, through our kind of uniform distribution of viscosities here, right, planets down in this corner, planets that would have lower intrinsic mantle viscosities, right, which is probably ultimately tied to their overall composition of the mantles, right. And so low viscosity means the planet convects more vigorously and therefore loses heat really quickly, doesn't hold on to its heat very well, right. So low viscosity planets tend to cool off more quickly and have volcanism die out more earlier on. Right, higher viscosities tend to hold on to their heat longer and have volcanism that lasts longer. And if you get unlucky and have a low heat producing element budget, right, naturally less heating power, you're going to die out earlier too, right? So the corner down here is the kind of worst case scenario to be in, right? And planets up here, this is sort of the best case scenario, lots of heating power, right? And the high viscosity allows the interior to hold on to heat for longer, right? So you can get volcanism and volatile cycling happening for billions of years, right, in this kind of corner. Right? Okay, so what we want to do with this, maybe I'll go back to this slide before talking through this part, right, is we want to take these kind of results and ultimately make like a prediction of saying, okay, if we observe a particular exoplanet based on these kinds of models, like how likely is it to still be volcanically active and driving volatile cycling if we observe it today, right? So that means we want to think about, what was that planet like when it formed X many billions of years ago, right? And so our probabilistic kind of idea of the range of heat producing element budgets a planet has, right? We have these distributions I showed earlier, and we were kind of treating that as the like random variation that you see in the galaxy today, right? But if we want to do this exercise, right, of thinking about, okay, if we observe a planet today, how likely is it to still be outgassing today, right, or volcanically active today, right? That means we need to know something about conditions when that planet formed, right, however many billions of years ago that was, right? So the question is, are these same kind of distributions of the heat producing elements we used for this figure going to be the same if we go back in time, right? And the answer is not exactly. There's another effect we have to consider, right? And that's this idea of galactic chemical evolution, right? So the kind of background composition of our galaxy has been evolving over time, and it evolves as stars produce various elements through nucleosynthesis, right? And so the various kind of ratios of things like the heat producing elements compared to the rock forming elements changes, and we would expect to see different kinds of heat producing elements dominating, right, as you went back in time, right? So I'll show plots now just to orient yourself. I'm a geophysicist. I'm used to thinking of like x-axis being time from like Earth's history, maybe 0 is when Earth formed up to like 4.5 billion years. This plot is now showing 0 is when the Milky Way galaxy formed, right, over 12 billion years ago, right? And a Milky Way galaxy of 8 billion years, that's when the Earth formed, right? So basically the different kind of breakdown of heat producing elements has changed over time, right? And so most of the heat producing elements we think of generally decayed, right? So this is thorium, right? The two uranium elements, right? While potassium actually has this kind of funky, right, curve where it increases a little bit, right, and then decreases, right? And this is taking into account both the kind of overall abundance or concentration of these heat-producing elements in the galaxy, but also how they're compared to the rock-forming elements that would go into making a rocky planet, right? Because we're really looking at the concentration of these elements in a rocky interior in the end, right? Okay, so a little easier to see with this diagram. All right, so this is showing how the heat budget of a planet, right, we get broken up into these different heat-producing elements at different times, right? So back up here, this is a planet that forms 12.4 billion years ago, so when the Milky Way galaxy forms, right? And at that time, uranium-235, right, which are the green bars here, was actually the dominant, kind of most abundant heat-producing element, right? So we think planets would have gotten most of their initial heating power from uranium-235, right? The yellow here is potassium-40, right? Yellow for potassium, because we're thinking of bananas have potassium, right? So we went with yellow, right? Cayman and I have called all of this work we've done on this the Banana Planet project, as we think about potassium being an important element, right? So uranium-235 for really old planets, right? Then potassium, right? And then thorium and uranium-238, right? So planets that formed very early in the Milky Way history, right, tend to have higher total heating powers, right? So like 250 or so terawatts is the median of this distribution, right? Compared to something more like, 100 terawatts, 125 terawatts for a planet forming at the same age as the Earth, right? Which are these guys. But most of this heating power is coming from uranium-235, which has a relatively short half-life of like a few hundred million years. So it doesn't really help us that much. We get a little bit of extra heating power, right? But it's from a short-lived isotope. So it's not such a big deal, right? Planets that form later on, right? Like the Earth or later, right? Their heating power tends to be more dominated by potassium-40, right? Because its uranium-235 abundance, right, has shrunk over time through galactic chemical evolution, right? Okay, so what does this mean, right? We're going to take these galactic chemical evolution trends, right, throughout galactic history, right, and use those to kind of shift our distributions of the heat-producing elements around, right, and run even more models, right? I think I ran literally millions of models for this. Like each model is actually really short. It takes like a second or two to run, right? So you can sweep through this huge variation in parameter space, right? And we're going to use this to say, as we go back in time, right, these heat budget kind of compositions change based on galactic chemical evolution, and we can take that effect into account as well. Right, so here's kind of the main punchline of this, right? So we've got the age when a planet stops degassing, right? So the planet age when it stops degassing, right? And I'm showing this three ways. So in the middle here, this is like the average of our uncertainty distributions. On the left here, this is the lower bound, right? So the planets that get unlucky and get very little amounts of heat-producing elements and so on, so they die out earlier on, right? On the right side, this is the upper bound of our kind of uncertainty range. These are the lucky planets. They get lots of heat-producing elements and get to stay active longer, right? And the trends are basically that, right? So here is, again, time of planet formation in galaxy age. Milky Way formed here, right? Earth here, up to today, right? And so as you go back, right, from today back in time in Milky Way history, right, our age when degassing ends gets a little larger, so like 2 billion years up to like 3 billion years, right? This is for an Earth-sized planet, right? And again, all still stagnant-lid planets, right? And that's just because of this galactic chemical evolution effect, where we get a little bit higher total heat budgets, right, from these higher, abundances of radioactive elements. But again, most of that's coming from uranium-235, which has a shorter half-life, so it doesn't do a whole lot. It's not like many, many billions of years longer, right? And then up here, we've got planet mass, right? Again, showing the same kind of effect I talked about earlier, that larger planets tend to hold on to their heat longer, so they stay volcanically active longer, right? So we've got these effects, right, again, mapped out for our kind of average of our uncertainty sweep of models, right, upper boundary and lower boundary, right? And basically we put this all together to then make a prediction of, right, what kind of planets based on their age and mass might still be volcanically active today, right? And so we made a marker here, right, we call it age max, right? So that's saying, like, based on our prediction of how long volcanism lasts, right, and then extrapolating this back in time and taking into account these galactic chemical evolution effects, right, we can draw this line and say, okay, planets, right, that are, at least 2 billion up to maybe 3 billion years old, depending on their mass, right, or younger, right, we have very high confidence that even if they have stagnant lids, right, and all the other kind of assumptions we put in the model, right, would still be actively volcanically active today, right? So we've got a couple planets to plot up in this field, right? Then we've got a lot of planets that are much older than that and plot down in our field where, I wouldn't take these results and say these planets are for sure dead and volcanically inactive and maybe geologically inactive, but you certainly can't be confident that a 8 billion-year-old planet is still going to be volcanically active and driving volatile cycling, today, right? Because that's a pretty old planet, right? So we drew this a couple ways. Here is from the average of our big uncertainty distributions. If we take the most optimistic kind of upper bound scenario, then we make this plot. There are a few more planets, right, that would plot into our potentially still volcanically active field, but still a bunch more that plot down here, right, where we can't really be very confident they'd still be volcanically active, right? I'm kind of being careful there to not say like, these planets are definitely volcanically dead, right? Because we got to remember, one, this is all looking at stagnant-lid planets, right? Planets with plate tectonics are probably going to be able to maintain volcanism for longer than stagnant-lid planets, right? And also all the assumptions I made in this model that I didn't bore you with all the details of, were kind of made to be pessimistic, basically made to make planets cool off and stop volcanism as quickly as possible, right? So this is meant to be sort of like the most conservative or kind of worst case view, right? So planets up here, right, you could feel very confident are still active. Planets down here, less confident, but we certainly can't rule them out. And I'll point out these planets here are the famous Trappist planets, right, which were discovered a few years ago, where there's this whole system of planets with a number of them in their star's habitable zone. Very exciting system to be studied. James Webb is like actively looking at these planets' atmospheres right now to see if we can see any signal for both habitability or even biosignatures. Our models would show like, they're pretty old, right? They're almost like 8 billion years old. There's big uncertainties. It's hard to date planets. Really, this all comes from dating the star the planet orbits, and that's hard to do, right? But it's worth just keeping in mind that these things are pretty old, right? And it wouldn't be shocking if they're kind of, tectonically or volcanically dead, right? And actually this Trappist 1b, it just came out like last week. There's a paper that just came out with the first observations, and they have no evidence of an atmosphere at all, right? They think it has no atmosphere, right? And it's actually it's pretty close to the Trappist star at orbit, so it might have just had its atmosphere blasted away over the years, right? All right, this is a good time to check time. All right, I can try to rush through quickly the last part. All right, so we're going to change topics a little bit for a couple of minutes here, and I'm going to show some brand new work, right? So this is the work Adam's been doing. And this is work that's like, we often say hot off the presses. This is hot off the press of Adam made a figure for me Friday. And I'm going to show you that because it's a really cool preliminary result. All right, so what are we doing? We're interested in waterworld planets, right? So obligatory old movie reference that came out way before most of you students were born. Maybe all of you students were born, right? The waterworld, right? So, we have pretty good evidence that there is a number of planets out there, exoplanets, that for whatever reason, just from the kind of, luck of the draw of planet formation, acquired more water than Earth has, right? It doesn't take that much more water to totally flood a planet's surface to where there would be basically no land sticking up anymore, right? And that raises some questions about the habitability of these planets, right? It raises questions like, can this same carbonate-silicate cycle still operate if there's no exposed land, right? So that's something I've also worked on in the past, but I won't talk about right now, right? But another question is, what about these bioessential elements, right? So on Earth, right, the exposed continents are a source of phosphorus through weathering to the oceans, right, which is a major nutrient for life on Earth, right? But what if we don't have any continents exposed because the water level's covering everything up, right? Can we still get phosphorus by reactions with the crust here into the ocean or not? All right, so what Adam's working on with Kim and myself is modeling the process of a hydrothermal system on the seafloor, right, like we have on Earth, and would expect to see on exoplanets as long as there is some volcanic and tectonic activity going on. All right, we've got hydrothermal fluids that come into the crust, right, react with the crust as they heat up, right, and then get expelled back into the ocean, right? And what we're looking at is the process of dissolving or weathering this crust as the water flows through, right? And then precipitation, right, of minerals. And we're interested in phosphorus, right? So we're mainly trying to track phosphorus release from alteration, right? And then whether it precipitates, which would remove it from the water, right, in the form of phosphorus-bearing minerals, which is the most important one that we're focusing on is apatite, right? And so that's going to control how much phosphorus we can get dissolved into this water versus locked up in apatite, right, to get back into the oceans and serve as a source, a food source for life. Right? Right, so this is really going to come down in large part to whether apatite precipitates or not. Right, so we've got water flowing through the crust, dissolving the crust. That's pulling some phosphorus out. Right, where we think phosphorus is mainly sitting as a trace element in minerals in the crust. Right, but if we then reprecipitate apatite in this pore space as the water's flowing through, it'll just suck all the phosphorus we got out back into apatite, and we'll have very little going to the ocean. Right, so we really care about, is apatite going to precipitate in these systems or not? And that comes down to, right, other kind of chemistry involved. Right? And what we're focusing on right now is we think calcium is going to be a big player in whether apatite precipitates and takes our phosphorates out or not. Right? So the main kind of types of apatite minerals, right, that would take out phosphorus all have calcium in them. Right? So what we're thinking is if there's less calcium in the crust that we're dissolving, there's less of this coming out, and it's harder to make these minerals. Right, and we keep phosphorus in solution and get that into the water. Right, so here's the figure Adam made on Friday, right, where he's varying the crustal composition. It's still essentially like a basalt, like an ocean crust, but we're playing with the end member minerals, right, in this crust to go from very low calcium content to higher calcium content. Low calcium content, we get high phosphorus in the fluids, right? Then apatite starts to precipitate because we get too much calcium. And boom, our phosphorus goes way down because the phosphorus is being sucked into apatite and not remaining in the fluids that go out into the ocean and can be a source for life, right? So we think this leads to I'll skip it. A very important control in the ocean, in the crustal composition, right, which is ultimately tied to the planet interior composition and volcanism, right, for whether we can get phosphorus in high quantities into the oceans available for life, right? Okay, so I'll wrap up there because I think we're probably right at about time, right? And leave you guys with my summary and conclusions here, right? So thanks for your attention.